We're going to start a new and very important topic, and that is to do more advanced things with C input and output. And that, of course, also connects up with some ideas about the operating system and how the operating system connects to file I/O. So that gives you a lot more power and flexibility in using your computer. Now, what have we done so far? Largely what we've done is use Printf and scanf. Those are two workhorses. They're fairly basic. Print goes to the screen. It uses standard out. Scanf goes to the keyboard. It uses standard in. We've also used occasionally what we call redirection, which is instead of going to the screen, we have this greater than sign, and then the output goes to a file. And if we have code.exe less than a file, then the file is providing input into scanf. So we've also occasionally made use of what's called file redirection, which uses a feature of the operating system. Now we want to get more sophisticated. So one thing we can do is learn more about Printf. Printf always has a control string, which is a quoted string, and that gives instructions either verbatim as to what's printed out on the screen, like hello world, or it has things with percents in them that do conversion of things that occur in a list of other arguments, and that's a comma-separated list of arguments. And here's an appropriate example. If we were to say printf sum of x and y is %d and %d equals %d, we would get on the screen sum of x and y is, say, x is 3, y is 5, x plus y is 8. And we would get 3, 5, and 8. The equal sign would show up, and that would be on the screen. And that's sort of the standard kind of thing we've already done to date. And that's where we've used %d as a conversion of one of these arguments. Well, there's lots of conversions. You haven't used the full number. Some are fairly obscure. For example, %sign is a way to print a %sign. So if you have a double %sign, rather than % with some character, you actually literally put out a %sign and you don't do a conversion. What we've generally used so far are things like D for integer, F for float, C for character, S for string. Those are what have been most used in this course. This is where we've already mentioned where you had two %signs or with a %. Now we can add to that something called format specifier modifiers. They include modifiers and control codes. This is a table taken from something at Sun OS. Sun Microsystems was a very famous producer of large-scale industrial strength computers especially that could be used with advanced graphics. The company, I believe, got absorbed. So I don't think you see many Sun machines anymore, but there's still a lot of software that Sun produced, and they had very, very good C compilers, and most of their work was in Unix using the programming language C. Then they later actually invented Java. Now, why are these modifiers useful? I put up a table there, you could see it. This is a standard thing where you'd print a character, let's say the character A. Here you're using 2C. 2 is a width modifier, and that is a width where it's pushed to a right margin, so you have a blank space and capital A. And you can also do it with a minus. And if it's a minus, you have A with a blank space. We've also used %D. So if we were to print 123, it would show up as 123. But if we do it with a width modifier and a first 0, it says, oh, however many digits you need to fill this space, the leading digits will be 0. So you see 0, 0, 1, 2, 3, because that's of length 5. So that's modifiers that do integers with padded zeros. And here is something where we modify and use an exponential way to write out a floating point number. And if that floating point number is 0.123456789, it's a little less than an eighth, you would see on the screen that the 12 would get you 12 spaces. The conversion here is such that we have an exponent part. So the exponent is -1. So that's why 1 is really a -1. So that really means this is 1/10, and that's 2 100ths, and that's 3 1,000ths, etc. And since it was 12, you would have a final empty space character. We're going to play with this for a second, show you how to do it. Of course, very straightforward, and it's a much easier way to capture these ideas because there isn't that much of a logic to it, but it really pays to experiment with it, see how the output actually appears on your own screen. And just keep in mind, clear output is a sign of intelligent coding. It's a saying from Dr. P. So let's go and look at and I've already written this program. There's a program to demonstrate a little bit of what we just saw. Here's your double, x equals that number. And here's some general, we're going to entitle it general printing ideas. So we have some literate expression on the screen. And now watch what I'm going to do. I'm going to show you how x would be expressed as that -12.5e, making sure that it does what I just said. We'll also compare it to just using a normal exponential without any modifiers. We'll also use a floating point way of doing it with some modifiers, which also has a space modifier and a precision modifier. So space is 10, precision is 5. And then we're going to do something which actually is a no-no. We're going to use the inappropriate conversion. X is a floating point number, and we're going to convert it to an integer, and we're going to see that that gets us what basically is an error, but would be very hard to understand, and it's an easily made error. So I've already compiled this. Let me run it. And there we are. So we can see here, this is using width of 10, and that's why there's a whole bunch of leading white space. And then this was a 10.5f. So we get these 5 significant figures. Here we get the ordinary use of E without any modifiers, so we get a much lengthier number. We get 1.23456, and the 7 is turned into an 8 because it was 7 and a fraction that was greater than a half, so that ups the conversion. So we're actually getting 6 significant figures here. Here we only got 5 significant figures, which is what we originally specified. And both of these are 10 to the minus 1. So that's why there's a 1 here as opposed to the way this floating point representation is. But here, look at this. Converting it to integer, we get something that looks like nonsense. Why is that nonsense? Because internally, that was stored as a 32-bit representation of a floating point number, and this is how it converts to an integer. So it has no relation. We don't end up with what you might think would be a 0. In other words, if I had said, let me in fact do that so you can see it. I'm going to go back. I will create a second program, print2 times C. I will incorporate and now what I'm going to do here is I won't change that. I'm going to change this, and I'm going to cast it to an int. So I'm going to compile. Run it. And indeed now we get this value 0. We get what we had mistakenly thought was going to happen before. Okay, and you should play with such code yourself and modifiers and all the various kinds of conversion characters to the extent that you want to learn in a deeper way how to make use of the fancier output formats that are available to you.